objective of this lab is to examine and understand the motion of a spring mass system in which the mass swings in an arc while also oscillating on a spring. In order to accomplish this, I will apply fundamentals of both momentum principle and energy principle in conjunction with other concepts like Hooke's law in order to create a model that will demonstrate the principles in relation to the spring mass system. We will see, in the end, that the spring mass system does indeed satisfy the energy principle. To begin, I used Tracker to analyze the provided video clip. I set the origin of the coordinate system at the fixed attachment point with the axes oriented so that the spring hangs in the negative y direction. I then calibrated the axis length using the known length of 0.7 meters from the attachment point to the length of the spring with the mass. I tracked its position as it oscillated and moved in an arc. Using the data that I obtained and is saved over here, I was able to solve for the period, or the time required for one complete oscillation, the spring stiffness, and the relaxed length. In order to find the most accurate period, I found the time it took for 3 oscillations to occur in the y direction and divided by 3. Here. I then manipulated this formula to solve for the spring stiffness given the period that I already determined. Finally, I was able to solve for the relaxed length of the spring due to the fact that at static equilibrium, the gravitational force acting upon the mass is equal to the spring force. Now let's look at the model that I created. The initial conditions were set here, the mass and the initial position given from Tracker, given that the mass was initially at rest before beginning its movement. The length of the spring is calculated here as the difference between the spring and the ball's position. And S here is the compression or stretch of the spring. This is important because it can be used to calculate both the spring force, right here, as well as the spring energy. The computation for each energy component must be done using their equation definitions before the loop is begun. The initial energies are then set equal to these values at the start of each iteration. We have to make sure we save the initial energies before we can make new motion predictions using the momentum principle. After the new velocities and positions are updated using the momentum principle, similarly in process as in Lab 3, we can, down here, finally compute the final energies and the energy changes that occur. If we choose to evaluate the system as the mass, spring, and earth, and using the energy principle, the total change in energy will be equal to the sum of the energy changes within the system, or the change in kinetic energy of the mass, delta K, change in gravitational potential energy, delta U sub G, and the change of the spring potential energy, delta U sub S. We consider the mass of the spring to be negligible, so it does not contribute to kinetic energy changes or gravitational energy changes. The interactions of the surroundings with the system will yield a change in energy of 0, meaning that there is no energy transfer. Alright, let's run this. As you can see, the comparison isn't too bad at all. The data that is outputted by the model is very close in the data that I obtained using Tracker. The red ball is a bit jumpy and doesn't appear to be exactly following the blue ball, and there are several reasons for that. First, the time between each observed position is 20 times longer than each predicted position. So it does create a smoother model, but the observed positions are farther apart and appear more static. Also, human error can account for inaccuracies when placing each position point in Tracker. Another thing to note is that I had to create an empty data point at the beginning of my CSV file to account for the fact that the initial calculated point is not plotted before moving through the while loop, and this discrepancy create a slight shift in the two graphs. When I did that, the graphs lined up almost perfectly, as you can see. According to the energy principle, the sum of the contributing changes in energy should be equal to 0, as you can see. As I ran through the loop of the model, it plotted the changes in energy, as you can see down here, in which the yellow line is the total net delta E. The total changes in energy are equal to 0 during the entire course of the oscillation or movement of the mass on the spring, which validates the energy principle, as we were trying to address. It also validates my earlier choice to consider Earth as part of the system, with negligible changes in contributing energies. In addition, evaluation of period is dependent upon axis that is chosen. As I have been observing throughout the course of the lab, the mass moves in an oscillation along the y-axis, yielding a period of 1.5 seconds. But the x direction is different, since we observing a pendulum motion as it goes back and forth in the x direction. We cannot expect that these two periods will be the same, especially since the formulas for determining them are different.